In this lab, we were given the mass of one star and told that it orbits around a black hole. We were then given a unique orbit and told to determine the net force acting on the star from the black hole. After determining the net force, we could then calculate the mass of the black hole. This lab shows the effect of mass and gravitational pull on any given object and is important because it explains how many of the objects in space interact. I found that in this case, the closer that the star was to the planet, the larger the gravitational force was that was acting on it. Some of the fundamental concepts in this lab is velocity, which is the change in position over the change in time in meters per second, and Newton's second law, which is change in velocity over change in time equals F net over mass, both of which we have covered in previous labs. Gravitational force is probably the most important concept to understand in this lab, and it is the force that attracts a body toward the center of the Earth, or in this case, toward any physical body having mass. The equation for it is the gravitational constant multiplied by the two masses of the objects divided by the distance between them squared. Another important concept in this lab is momentum, which equals mass times velocity, or F net times change in time. The change in momentum can be broken down into its perpendicular and parallel components and is represented by dp over dt. The sum of the perpendicular and parallel components equals the total change in momentum. For my glow script code, I began by setting my initial conditions. I changed the star's mass to the given value of 2 times 10 to the 30th kilograms and then changed the time interval to 1 day in seconds. I then began my calculations. We first had to find the initial momentum and final momentum, which were both the star's mass multiplied by the corresponding velocity. Then the change in velocity and the change in momentum were both set to equal the final minus the initial of those values. Following this, I set F net to equal dp dt because the net force acting on an object caused its momentum to change. After this, we had to find the parallel component of dp dt, which was the tangential change in momentum, so that it equaled the magnitude of dp dt times p hat, which was the unit vector. This was set to equal the parallel component of the force. Following this, we calculated the perpendicular component of dp dt by subtracting the parallel component from the total dp dt. This value is then set to equal the perpendicular component of the force. Now it's time to calculate the mass. Using a rearranged gravitational force equation, we could calculate the mass because we knew the net force and the displacement for any given location along the orbit, in addition to our set gravitational constant and mass of the star. This ended up giving slightly inconsistent values of mass for each location, but this was simply because we could not use exact calculations for the net force and displacement. The values were all similar, and when I averaged them out, I found the mass of the black hole to be 1.7 times 10 to the 34th kilograms. I then created the video to represent the path of the orbit. I added arrows to represent the different forces acting along the object's path, and I'll play this video now. The blue arrow represents the parallel component of the force and points tangentially throughout the orbit. It switches its direction halfway through the orbit because the object goes from accelerating to decelerating due to its displacement from the black hole. The pink arrow represents the perpendicular force and it points inward, perpendicular to the kissing circle of the orbit at any given location. The last force is the net force in orange, which is the combination of the parallel and perpendicular components of the force. Therefore, it falls in between these two arrows and points toward the black hole, maintaining the oval-shaped orbit of the star. Overall, I found that the star accelerated for the first half of the orbit, but began decelerating after reaching its closest point to the black hole. This means that the closer it was to the black hole, the stronger the gravitational force was, causing the object to accelerate and have a positive change in momentum. The momentum principle tells us that the net force is equal to the rate of change of momentum. These are not the same concepts, though. F net is found by analyzing the forces acting on a system, while the rate of change of momentum is found by studying the motion of the object as it moves along a certain trajectory. However, as previously mentioned, if you know one of these, you can update the other, but they're not necessarily the same. If we are told that the black hole was replaced by another of different mass, but the motion of the star remains constant, it's not possible to find a value for the new black hole that is different than the original. We know this because if the orbit of the star is not changing, this means that the position data points and gravitational force acting on the star is also unchanging because of the gravitational force formula. If we do not have any changing inputs for the variables in that equation, it would be impossible to determine the mass of the new black hole. In the future, if I were to do this lab again, I would try to use the non-rounded numbers to calculate one consistent mass value for the black hole instead of slightly different values. I would also be interested in exploring what happens to the orbit of the star if you changed the different values within the gravitational force formula.